Good afternoon and welcome to the CERIAS Security Symposium at Purdue University. Our speaker today is Ron Buskey, Fellow of the Technical Staff for Motorola. And I'm proud to say that Motorola is a member of the CERIAS Industrial Partnership Program. Mr. Buskey heads Motorola's Security Architecture and Research Laboratory. He's been with Motorola for 21 years with a variety of software and systems responsibilities.
Thank you, Joel. Just to kind of a little bit of introduction about who I am and my background so you have some idea of where I'm coming from today. I've been at Motorola 21 years. I spent about 5 years with General Electric before that. Back in the early 80s, I spent a little bit of time with a software startup, kind of before the dot-com craze got really started, but so I've had that experience. Involved in software development, involved with managing software development teams from a few people up to about 50 or so. And also very much involved with the software development process as well as security components. So I've developed software for secure telecom products for the military and government use, so I've been at that level. I have developed software for factory automation, for business systems, finance systems, and been involved with security architecture work in terms of actual product development as well. So I've had a fairly long background over the years of looking at both software development and security architecture feature sets. And what I want to do today is spend just a little bit of time talking through some of my observations about why it's a little bit different looking at what software engineering is and what happens in the security realm, and why sometimes those forces go a little bit different directions and things that you might want to be thinking about. Now, if I hit my target today, what I expect to have happen is a few of the things that I say, each one of you hopefully will say, yes, I've thought about that. That's interesting. You know, why would he bring up that point? But if you only see a few of those points, that means you've been thinking about this kind of a process. Hopefully none of you will sit there and say, well, I've heard all of that before, because that means I'm bringing nothing fresh and new for you to try to think about, so we'll do that. It's my understanding we can be a little bit interactive today, so I welcome questions. Feel free just to stick your hand in the air or yell at me. We'll take it. I will use kind of speaker's prerogative through the course of the day. So if you ask me something and I think it's a little bit more in depth than I want to get into, I will be here for a few minutes after the talk, and I'd love to debate the object after the session. So what I want to do is spend about about 2/3 of my time this afternoon talking about my observations. What is it that's different? What's the tug and pull between security and software? And then I want to end with an example of a program or function that's been recently done within my lab that kind of touches on some of these areas in terms of an embedded system and embedded system development, and about why that's important. I'm only going to just briefly touch on what's going on in that space, but we do have some context, and I'll provide some links at the end of the talk on where you can go to get more information on that. So what I'd like to do is introduce the concept of the environment that I'm dealing with. What is it that I mean when I talk about an embedded device? Because a lot of people today have an opinion or an approach that they think that they mean by an embedded device, but I want to talk about what I mean. So I'm talking about a system that's going to start with 4 processor cores. Now, these are independent processors, typically within the same device. These devices will have at least 5 separate network interfaces. And by separate network interfaces, I mean I'm dealing with a voice circuit call, I'm dealing with an IP data traffic, I may be dealing with a Bluetooth, local area or PAN networks, I may be dealing with things like USB connectivity or time-sliced short message kind of capability. There are 5 separate interfaces. Some of the products we're dealing with may have 2 or 3 more beyond that as well. Typically, I'm talking about at least 2 separate operating systems. Maybe looking at a real-time OS like Vertex or something of that nature. Maybe looking at Linux, Microsoft Mobile, Symbian functions. So typically, these are going to have a mix and match, at least 2, sometimes more, running on these multiple cores. We're talking about a significant amount of memory, in the order of 2, maybe 300 megabytes fixed, the ability to put a gig, maybe 2 gig on these devices from a fixed removable media where I can pull it out and put it into another system. Talking about a device that probably has at least 10 million lines of code. Now this is probably a conservative estimate. The problem is it's very difficult to capture how many things are going into these devices all at the same time. But it's a lot of code, and these are very complex systems. I'm also going to introduce the concept of having 2 separate security models. There's one model that's fairly traditional within the electronics or consumer electronics space, which says that I am protecting the network or the service provider, their services, from the end user. The end user may in fact be the adversary or the attacker in these kind of cases. So what we're seeing is I have services, I have feature sets, I'm delivering this capability into my product, and I'm concerned that the end user who's holding the device in their hand has full access to it and may be able to attack it to get free service or to circumvent functions or to disrupt my network. Now the second security model is pretty much orthogonal to that, and it's the other way around. I'm looking at information that's being presented by the user, owned by the user, and their concern is what's going on from the network. If I have information and connectivity coming in, is someone going to download a virus? Is someone going to give me a Trojan that's going to suck my data out? And in fact, I may not trust the network operator that I'm connected to because they may actually be the attacker, or their system may be subverted by an attacker and be coming after my system. So how do you look at these two specific security models that are very much different, because neither side essentially trusts the other side, and establish a security trust model in the middle? Motorola's been looking at some of those kind of questions, trying to understand who is it that can become that trust agent that both sides can trust to be able to protect their individual stakeholder interest in this kind of device. So what is it that I've been talking about? Talking about a cell phone that looks very much like this. This is a fairly recent one. It came out onto the market just in the last couple of months. You may have seen our advertisements for it, but that device has all these characteristics. When I talk about an embedded device, that's what I'm looking at. And a lot of people are not aware that the complexity that goes on inside of that system. So let's take a look a little bit at what is it involved in doing software engineering versus security engineering. So when I talk about people doing software engineering, typically I'm referring to people that are out there that are doing things like defining use cases, looking at requirements capture, defining testability to meet those requirements, developing interfaces, building architectures, and writing software. And they're probably going to go at that in a very iterative process. They're going to write some requirements, they're going to look at some use cases, they're going to build some features, they're going to test it. I can do more. They're going to write some more requirements, some more use cases, and that's going to keep on going. Typically, when I talk to software developers or product developers, they're asking the question, what can I make this device do? What can I do in the market space? Conversely, I'm talking to security engineers, and they're looking at a different set of skills. They're trying to define assets, what's important on the device, looking at the abuse cases, what can I make this system do badly if I touch it, probing the interfaces to see, is there weaknesses in the interface itself, can I extract information. They're looking at cracks in the system, what can I do to get myself in between specific functions. They're doing risk analysis, trying to do trade-off between cost effectiveness and what they're doing, and developing threat models. So if I ask them what their primary job function is what can I make this system do wrong? Now the problem is, if I go into a software development or a product development team and I ask them, who's responsible for doing your security work? The answer I very often get is, oh, Tom and Bob over there kind of think about it on occasion because they've got a little bit of experience and they took a course. Now the problem is that Tom and Bob are doing the things that you see on the left. They're defining use cases, they're writing requirements, they're meeting interfaces, and they're building software. That's what they do, that's what they're paid to do. The problem is that I don't see any overlap between the skills on the right and the skills on the left. So if they're spending all their time thinking in one mode, to ask them to spend a few minutes a day or a couple of hours a week thinking like this other hand, they may do okay because they're really smart people and they're really good at doing things and they're very aggressive at functioning. But guess what? Very good may mean if there's 100 vulnerabilities or 100 open issues within that product, they may find 98. That's okay. Is that good? The problem is that the adversaries that are out there looking at trying to break into these products are still going to have two. And that's not acceptable in most of these cases. So the problem is that we're trying to understand within the problem and domain set that we really need to see the trained professional security engineers that are not spending most of their day developing software, building systems, identifying new product features, but they're looking at these issues from a security standpoint. We have to be able to do this. And that's one of the reasons why we're very much targeting programs like CERIAS here at Purdue, because we believe that they can help train some of these people to bring into our corporate settings and our corporate situations. One of the issues that we have to look at then is the boundary structures. So if I look at a very simplistic diagram for a product, what I'm looking at is things like I have processors, I have memory, I have I/O devices, I may have a couple of different chips, I've got modem stacks and applications and all kinds of user frameworks, and all that stuff is good. And we're learning how to apply tools to look at a lot of these things. I can look at a static analysis tool to analyze an application and say, is there buffer overruns in it, or misuse of data, or tag information as I'm processing it through. I may have people that are looking at the operating system trying to figure out how to do robustness functions so that I have isolation in virtual machines. I may be looking at user environments and frameworks that allow me to put applications into those kind of spaces. But very often what I'm not seeing is what's going on in the middle of all these components. That's where the security problems all lie. As an example, about 2 years ago, there was a series of papers actually published, I believe it was at the RSA conference, where someone took a system and they were running AES with a strong key. They didn't try to break the AES, they didn't try to break the key. What they did is go down at the processor level, look at the caches in the system, identify where tables for the algorithm were being loaded, and then use the timing through that part of the system to actually extract the keys. They were looking at those individual cracks, the boundary conditions between the functions. AES was not broken. AES is a strong algorithm. The keys were sufficiently long. The application was written reasonably well. But they didn't take it into account the fact that they had to look at all of the components on the system at the same time to be able to do that. One of the concerns that I had, in fact, we had this discussion at lunch today, is that one of the problems that I'm seeing in our education system, especially in software people, we're training them to look at things like abstraction. Look at how do you build very large, robust software systems, and appropriately so. But the problem is when I take a software person and start to talk to them about doing security components and analysis, they don't know what's going down underneath that abstraction. Very often they don't even know what's going on in the operating system, let alone down in the hardware. So if I go to a software person and say, what's happening with this information stream, what registers is it going through on the processor, what buses is it touching, I very often get a very blank stare. They don't know. My problem is I'm seeing a lot of older people like myself that have been around for a lot of years in this industry. We had to build hardware. We had to write software. We had to look at things like register components. Probably aren't too many people in the room that's ever taken a very small processor function, used a hex keypad, and actually typed all your code in that way. Some of us that grew up when we went to universities and took training classes, that's what we did. We had a very good understanding of that. The problem is I don't see the hardware people and the software people really looking at those kind of interactions today in a way that I think the security organizational functions really need to take place. As an example, we had a product team come to us recently, about 2 years ago, and I can't describe exactly which product it is, but I think you'll get the gist of the concept. What they did is they had purchased a platform or a set of hardware and software stacks from a third-party vendor and put it into a system. This system was essentially designed to take voice communication between point A and point B. The problem that they encountered is they identified the fact that there was a software bug on that third-party stack on the processor. The result of that particular software bug said 10 months or so, give or take a couple of weeks, after that particular device was deployed, that bug would get hit and it would die. It would no longer turn on, rather catastrophically. So the problem is they had millions of these devices in the field, and all of a sudden they're looking at their calendar saying they had this ramp up of sales and installations, and that was really good. They realized that 10 months later they were going to have this massive ramp up of failures, and every device that was out there was going to come back in. So they came into my organization and said, we don't have any way to fix this other than a massive recall, bring every product back in, it's going to be very expensive. Your team understands things like viruses and Trojans and so on. Is there any way you can write a virus to go into our product and make this change? It was a very interesting problem. They said, oh, by the way, you only have 6 weeks to figure it out. My team started. We looked at it. We said, the first place we're going to start, all those gray areas. What's happening on the system? We looked at the inputs. We looked at the protocols, the network interfaces. We said it's primarily a voice traffic. Oh, somebody put in a little piece of code that allowed essentially a modem function to do digital commands to the device. Interesting. What can you do with it? What happens if I send a malformed command down that interface? I tell it I'm going to send it a data packet. It's going to have 100 bytes, and I send 200 bytes. What happens? Well, the immediate response from the product group is, you can't do that. And I said, I didn't ask if I could do that. I said, what happens if I do that? You can't do that. Why not? You can't get certified. So I'm a virus writer. I don't care if I get certified, neither do the attackers. That's the space they're going to start. So we started looking at that function. We said, Yeah, if you put a particular message down this pipe, tell it it's got 100 bytes and send 200 bytes, it walks from the stack over into the next application. Very interesting. What can I do from that application? Turned out from that application, I could exploit a problem in the operating system and actually open a channel to another processor. Oh, cool, what can I do with that? So I pushed some data through that channel to the other processor, found an application that I could touch over there, put my data up in that area, then what could I do? Well, it turns out that guy could make a call back to the first processor and actually invoke some software routines to update flash. Now that's a short version of what we did in about 6 months. So I was able to take this particular system, I was able to play a file, update their software. So if you happen to have one of these devices, you can answer the device and say, I'm in a voice call, and all of a sudden you hear a little noise because I'm playing a WAV file in the background. Your system would stop for a few minutes and reboot. When it came up, it had different software, and guess what? It wouldn't fail after 10 months. We looked at all of that space around that, each one of those interfaces, and the problem was the product organization that was involved in that particular product said, it can't be done. Why? Because they very tightly controlled what happened in the application. They tightly controlled what happened in the stack. They tightly controlled what happened in the operating system, and not a single one of them ever looked in the spaces in the middle. And that's where we have to go. That's why I really believe it's critical within our training programs, we are looking at this ability to train people that are thinking about careers in the security space. Think about the gray space. Whether that gray space is between applications and between layers within a small system, or whether you're dealing with it in a massive overriding network, it doesn't make any difference. That's where the problems are going to be. We've learned how to put things like algorithms and encryption functions and MAC layers within our capabilities. Now we need to start looking at those cracks. Next thing I want to do is answer this question, why is Y bad? One of the things that I often talk about with my product groups, and it usually gets me in trouble, is I say, if you're asking the question why, you've probably already lost. They don't like that. The reason why I think that's an important thing that we have to be very cautious about catching is because it brings down the fundamental issue of what is it that I'm concerned about within my product. If I'm doing security functions, I'm going to be doing a couple of things. First, I want to define my assets. What's important to me and what's it going to be that somebody else might be interested in? I'm going to establish the threat model. How is it that they can get into my system and what can they do when they get there? I want to evaluate all those boundaries and gray spaces that I was talking about earlier. The next thing I'm going to do is start to develop a cost model. What is it going to cost me or my customers if I lose or have my assets compromised? What is it going to cost me to protect it if I'm not doing enough protection on the device? And the third thing we have to look at is what is the cost for someone to attack my system and get at those assets? So these three cost functions begin to form the analysis points for risk analysis. For the last number of years, probably the last 7 or 8 years, I've drawn a chart that essentially shows a block that says, here's the amount of functions that I can lose, here's what is going to cost me to protect it, and here's what's going to cost me or cost an attacker to come at me, and when do I get in balance is what I want to do within a product function. So for instance, if I have an asset that's worth $100 and it costs my adversary $200 to get at it, they may be able to physically get at it, but I'm not going to see a lot of loss that way. People are not going to typically spend several $100s to get at $100. But if I have an asset that's worth $100 and they can spend $2 and get at it, I guarantee it's going to be lost in a whole lot of time. So then I have to look at what it's going to cost me to protect it. If it's going to cost me another $100 to protect it, I have to be very careful from a product standpoint that maybe I just need to change my business model because the risk may not be worth it. I'm going to do this analysis, this trade-off between these various cost models, and then generally I'm going to have to establish a roadmap for the evolution or the revolution of my protection functions. What's going to happen over time is our products are going to increase the value. My assets are going to definitely increase. Every year we come out with new things, new capabilities, new services, and every one of those are bringing value to the product. That's their purpose. So the value is going up every year. Now my adversaries are getting better, faster, cheaper tools, so their capabilities, they're coming up and their cost to attack is going down. So if my value is going up and their cost to attack is going down, that means I've got this bigger and bigger gap, which means every year I've got to do something new, different, and unique. So it's going to be an ongoing process. Now you'll notice that no place in here did I ever ask the question, now why is somebody going to attack my system? So typically when I'm dealing with a product person and they want to focus on why is somebody ever going to attack my system, they're not thinking about these issues. What is it that I can lose and how much is it going to cost me and how much is it going to cost somebody to come in? I am concerned about how much the cost is and what that balance is. I don't care why they're going to do it. They may do it just because it's there. They may do it because they can sell it. I don't know if you've seen recently, but there have been a number of things published in the last probably 6 months. There's a new site up, essentially an eBay type site, that sells exploits. People find them in products. Then they put them up for auction to see who wants to buy them. They don't care why they're doing it. They just are concerned that they can find them and then that they can make money on doing it. So their purpose and drive is to make money selling these exploits. Who wants to buy these exploits? I don't know. Might be a competitor trying to take me out of business. Might be somebody who has revenge, a former employee that didn't like being laid off last year. Could be a whole lot of reasons. Yeah. Question.
Yeah. Have you heard about the iPhone being hacked?
Yep.
Has that influenced your team at all?
Nope.
Ron, you may want to repeat the question.
Okay. Yeah, I think they've got microphones back there, but I'll repeat it. The question was I aware of the iPhone and the attacks on it to essentially remove it off the AT&T network and move it, as well as change some of its feature sets? And the second part of that question was, has it changed the impact of what my team is? And the answer is yes, I'm very much aware of it, because that's a part of the industry that we watch very carefully. 2, we expected it. And 3, we have been dealing with similar problems for probably 10 years within Motorola, trying to keep those same types of lock controls in place. And we think we've done a much better job. Of course, we've got 10 years of background where Apple hasn't only been doing it for just a very short period of time. So, yeah, I don't think it's changed what we've done. It has strengthened the things that, yes, we're aware of that space, and it's an ongoing process. In fact, one of the things that we did do a couple of years ago, we did a study in Motorola phones to try to understand what was the community of people of interest in, kind of doing, gray market or black market kind of work. And the answer was they thought the general community was about 6 million or so for Motorola phones. People interested in either attacking or using attacks on phones. We narrowed down the environment to about 300 to 500 actual, real life smart people that are actually doing attacks on a regular basis, trying to figure them out, trying to sell them on the internet, and so on. In fact, we've been tracking one group that we're very much aware of, and I won't give too much data on it. But a couple of years ago, we had some intelligence that said they had about 34 to 40 full-time people doing nothing but attacking our phones. Okay, so that's the kind of stuff. So we've been very much aware of those kind of situations. So once you've gotten past that, the next question then, and I kind of alluded to it already, is are we there yet? If I look at what security is looking at within most of these products, I'm looking at software and hardware features. These are becoming smaller, faster, cheaper by the month. Features and functions are being thrown onto our products a lot. If I look at a cell phone a couple of years ago, it made nice calls. If I look at a cell phone today, well, let's see, it's got cameras so that I can take pictures. It's got a video camera on there. I can do video editing if I want to on a small screen. And I don't do that, but I think there are people that claim that they do. It can do your email. It can do music. It can do whatever you want to on that little device. And all of that is just coming faster and faster and faster as the hardware gets smaller and cheaper. But as I said, the attack tools, the equipment to do that attack tools also are becoming smaller, cheaper, faster almost every year. We have significant pressure from our competitors. Somebody like Apple comes in with the iPhone and introduces a new kind of paradigm in how the user interface should work. Everybody has to scramble to put that on top of everything else that they already have. And consumer expectations. All it takes is for a group of people to say, I really like that particular feature in that particular product. Everybody else has to run and do it. These things are getting bigger and bigger and bigger all the time. From a security capability, they're under continuous attacks. As I told you, we already have this rather sizable community of people that are very interested in figuring out how to break in to products. They can steal features, they can get services that they don't pay for, they can put stuff in that they think is cool but maybe has some adverse effect on the network. And it's a very changing environment. So our problem is if I build it today, probably in 6 months, 12 months, 18 months at the outside, it's probably not sufficient anymore because of these constraints. So the product team that's used to going into a set of software developers and say, build me this feature, I put it on my product, thank you very much, go on to the next one, and they're done, are used to that kind of approach. In the security world, I come in and say, here's an approach that'll protect these assets. Thank you very much for putting in. 12 months later, I'm back to that same product group. Here's a new way or an improved way to protect those same assets. And they say, well, we did that last year. I say, well, that's true. You did that last year, but you're not doing it this year because the attack tools and the adversaries have gotten that much better. You need to improve and change it. So it turns out that if you're in the security field, particularly for the product level, that's okay, because that means if you start now, you'll probably still be doing it by the time you retire. So as long as you don't feel like you have to be a type of person that says, I did it, I'm done, I can move on, that's probably all right. You don't really want to be in this field. If it's okay to have that constant challenge and constant motion, this is probably okay. So that's kind of the attitudes that we're seeing. We're looking at those kind of functions and why those things all kind of wrap up together in the way we're doing product analysis. What I want to do is just kind of very briefly introduce a project that we've been doing in my lab for the last 2 years or so, and that we're just getting kind of close to that point of bringing out into the open market. As I said, I can point you to some additional papers and stuff that we've written on this topic. If you have an interest in going into some more detail, I'll just try to introduce it to here. One of the elements that we have inside of processors, and if you're not familiar with this kind of a processor approach, I'm going to introduce a JTAG, an in-circuit device emulation kind of function. And so what this does inside the processors is you have a tool for doing debug functions. And if I have that tool, that's really, really nice from a software perspective, because over in my processor, I have things like registers and address functions. I have peripherals that have data and I/O devices, my program counter, and all that nifty things. If I'm working on especially a small device like a cell phone or a portable function, I may only have a screen that's about 2 inches high, maybe a couple of inches wide, and it's really hard to embed a lot of printf statements to try to figure out where my code goes. For those of you that write code that way in your classes, you'll understand what I mean. So my software tool has the advantage I can extract all that information out to my software tool. I can look to see what data is in those registers. I can understand what's in the program counter. I can set breakpoints, say run to this point and stop. Let me look at what all's going on. I can manipulate those registers. I can change them. I can force them to go to certain values. From an attacker standpoint, an adversary in a product, this is probably also the #1 most powerful tool they have in getting into most products. Why? Because they can set it up, you can start the processor, you can single step through the code, you can see exactly what's going on. They may run all kinds of obfuscation techniques, have very poor structure, doesn't make any difference because you don't care. All you want to know is that the code is walking through a sequence of events and you can see what's going on. I have a piece of software that says, ask the user for a password, go verify it, return pass or fail. If I'm watching it through this kind of a tool, that's okay. When it gets to that routine, I say, go do that, break when you get back. In reality, and this is why I said it before, it's important to understand the differences. That pass or fail piece that you put in your code, whether it be Java or C code, is down at a register. It says if register 3 is 0, go over there because you've quote unquote passed. If it's not 0, go over here because you failed. But I can change the register 3 to whatever value that I want. I don't care whether I pass the particular password function. I just walk over there, and now I can execute that code. So from an attacker standpoint, this is a tool that allows you to have full control of a device. By the way, if you're doing security functions and you're doing cryptography and keys, if you're doing it in software, those keys walk through these registers. So if somebody has a tool like this and they want to know what your key is, they just have to watch the registers. There goes your key. So be aware of what can happen in this space. So we've introduced a concept that we've called protected JTAG. JTAG is the IEEE standard definition, 1146 I believe it is, that defines how you interact with this kind of function. So we're introducing a change called a protected JTAG. Protected JTAG essentially breaks this line from the software tools into the JTAG port in the processor. So now when I'm running code, I have all of these register informations in the processor. I don't see anything at all in the outside world. The traditional choice given to most product developers gave you two options. You could either eliminate JTAG, take it off, which meant all your information inside the processor was secure. People couldn't use these kind of tools to see it. However, your software developers didn't really have much of a clue what was going inside this box. Apply power to your processor and nothing happened. Where did it go? No clue. So you had to do things like build special versions or something of that nature to try to figure out how to get at that and hope that your special version acted exactly like your normal version. Otherwise, you didn't necessarily know what's going on. Or you go into your product development team and say, I'm going to let the JTAG function be there. Here's all these software development tools. Get it done faster, better, cheaper. That's great, but we're going to have to live with the fact that attackers out there and our adversaries are going to have this to attack our products. So we've added a new component to this called a secure server. And this is an interesting standard approach. We looked at it from, what is the normal security area that you would want to do this? Obviously, if I can do a random challenge and response kind of capability to a user, I can authenticate that he's supposed to be there and be able to do this kind of a process, which is fine, except that within a small device with very little capability, how do you actually do that? And that's a problem that we've been working on for a while. We believe we finally have gotten to the place where we have a very solid understanding in that space. So for instance, now we not only have the ability to control that connection point, but I can control levels of access. So for instance, I can give Joel, who is sitting there, access to be able to see registers 1 through 10, but maybe not modify any of them, just absolutely watch them but not see it. Maybe you can't control the program counter, so you can't change the way the program is flowing. You can just see some of the information. Maybe I don't let you see some of the key peripherals. I can then go to the next user, and I can give Bob over here the ability to control the program counter and some of the registers, but maybe he can't see some of the peripherals because that's not his responsibility. And I may have another guy who is the top person fully trusted in our organization. He's the only one that can run this tool to see absolutely everything. So I can control that in a granular fashion using this approach. The way we do that inside of an access manager, so I have this function called protected JTAG. I'm going to start by adding a random number generator, which a lot of these kind of chips typically either don't have or don't have a very good one. I'm going to be able to take a permission level from the outside world in, and I'm going to be able to then build a message. And a message, and I'll go through in a minute what that message looks like. I'm going to take a public key because I'm going to rely on some public key type infrastructure where I can take that public key and encrypt this message so that the device knows what it is, and the only one that can decrypt it, that can do anything with it, is going to be the person holding the private key out there in the infrastructure. That's going to then form my challenge. I can push that challenge out to the tools that are working on the middle. They can go to the secure server. The server can deal with it and then bring back a response. Inside the device, I can go through a verifier. I bring my original message into that verifier, the response into the verifier, public key is available to that verifier. If everything matches, then I can turn his permission controller on. I can set these levels, what signals can be controlled inside the processor, and once that happens, I reopen my JTAG interface at the appropriate level, allowing the appropriate feature sets to go out to these user devices. So some of the problems that we had to touch. First of all, you had to be able to meet the JTAG functionality within this capability. You had to be able to allow an appropriate user to have full access to this function without any restrictions for what they could normally do. Otherwise, you start to change every tool in the market space, which is not really feasible. You also wanted to have these different permission levels, be able to granularly change that in terms of I have different responsibilities for different parts of the organization. The other thing we very often talk about in doing protocols is what if there's a man in the middle and how do I protect against that? Well, remember the picture that I showed that my chip is over here and my server is over here. Not only might I have a man in the middle, I have to count on the man in the middle to make the protocol work. How do I maintain robustness in that kind of a solution? The other thing I have to be able to do is this has to be a hardware-only solution. I have talked with a number of people in the industry, and their approach was, well, why can't I just pass some certificates to my processor, check the certificates, and if the user has got a good certificate, I let him in. Well, remember what I started with, is that this particular tool can touch the processor from the time it comes out of reset. I'm watching the registers. I can single step it through. If the register that's holding the value that says I passed or failed my certificate check can be modified by the user at that point, which is part of the reason for this tool, they don't care whether they have a valid certificate or not. They're going to force the condition and they're in. So this really can only work if you have a piece of hardware that's on the system before your processor ever starts. And therefore, from a standpoint of dealing with real products, that means I have to minimize the gate count, the square area of the silicon, and I have to reduce the cost to make it a specific function. So in order to meet those requirements of trying to minimize the gate count and cost, I had to look at a protocol that was going to be very effective in hardware. It had to be small. We specifically looked at some of the elliptic curve mathematical functions because we thought we could meet some of those. But typically, if you're going to have to do those verification and encryption functions in elliptic curve, if you're familiar with that approach, typically you have either point multiplies, scalar multiplies, and inversion in order to be able to do those operations. And our problem was the inversion is huge in hardware. So we looked at this protocol from a function. How do I make it very secure? Can I move the inversion step out to the server that has a lot of horsepower and still maintain the security components down at the lower levels? And so we actually have a protocol that we believe will meet that in a secure fashion. And it also has the ability to handle these multiple levels during the process. Let me just walk through this briefly. Again, just kind of give you a flavor of some of the things that we did. If you have some interest, we can touch on it later. So I have 3 points to the system. On the left, I have a chip that's going to have this protected JTAG function. The middle, I'm going to have a set of workstation and tools that are going to be talking between the chip. And on the far right, I have my secure server. So within the protocol function, I'm going to use the following notation. I have P, which is a point on the elliptic curve. I have Q, which is my public key, and I may also have Q prime, which I'm not going to really talk about today because we also worked on a way to store only a piece of that public key for verification. Because if you have a programmable function that allows you to do that, those tend to be very large structures in silicon and very costly. We did work on a way that allowed us to streamline that down to about half what the existing art was in that space, so I could store a very small piece of key, yet guarantee the security proof that it was sufficient. In the middle, all I'm going to have is my user credentials on who I am and what capabilities that I possess. And then up at the server, I'm going to also have the A, which is my private key, and then I'm going to have the relationship that Q is equal to AP, which is a standard theorem within the elliptic curve map. So I'm going to start on the chip by generating 2 random numbers. I'm going to generate K and R, and you'll see how I use those in a minute. And then I'm going to accept a level L from the user at the workstation. And if I'm using this partial public key function, he's also going to process me the entire public key Q because he has a big disk on his workstation and he can pass that to me. There's a couple of techniques that we'll use to verify that the Q that he gave me is in fact the real Q that I'm expecting. Now this level is optional. In some cases you may only have an on-off condition, but in most of the devices we're concerned about, we typically have as much as 32 levels of permission based on these multi-core chips. And again, the Q is only going to be used if I'm using the partial storage. From there I'm going to build a message. I'm going to start with a header. This next element is the permission L times my public key. I'm going to use the X component of that. So if you're familiar with elliptic curve notation, I have an X, a Y, and a Z. And then I'm going to concatenate the random number R and the value of L. Now the reason why we do L and LP of X in the same function as part of the message is that gives me 2 different independent arithmetic statements that allows me to manage this man-in-the-middle condition. In terms of relative sizes, my R is going to be roughly 180 bits. X I'm going to take about 100 to 112 bits, and then my L is going to be someplace between 20 and 32 bits. From there I'm going to generate a challenge. And so if you're again familiar with elliptic curve functions, my challenge is going to be K, which was my random number, times P, which is my elliptic curve point, the message times KQ of X, which essentially is the encryption step of the message itself. And I'm also going to pass KQ of Z, which is going to allow me to avoid doing the inversions down here on my chip and move that up to my server. That challenge is going to go to the workstation. The workstation will then take that challenge, pass the original level that he's asking for and his user credentials up to the server. The server has the opportunity then to calculate M prime. So M prime is going to be MKQ of X. Remember, that's the middle term of the challenge. Divide that by KQ of Z, which was the third term of the challenge. And then it's going to calculate AKP, which is the private key that it owns, plus the KP, which was the first message of the challenge. If you divide all that back out, what you get is, assumably, the same message that you started with. From that message, we're going to extract L prime, R prime, and M prime. And we're going to verify that the user credentials is valid for the device they're talking to at the permission level that they're requesting, and that the level that they're requesting matches the level that the chip thinks that they're requesting, so we can make those 2 match in time. So L must match L prime, U must be valid, L prime and LPX must match, and also we had this little piece called the 0-1 header, which is in there for a couple of mathematical issues that we have during the translation of that protocol. If everything matches and the server decides that it's okay to allow and grant permission, it's going to calculate a verification token, which is M prime AKP. Again, M prime was extracted, and again, only the valid server that had the appropriate private key could get to that. times the private key times KP, which was originally came from the chip. The user just simply passes that to the chip, and the chip looks at MKQ, which is the numbers that it has, and if those two match, you can guarantee from a security and cryptography point of view that the server that held the private key is authorizing them to get access. If that matches, you simply open the gates, allow the L to connect for that user to go in there. So that's a way to look at that. Again, we had to be careful about how do you look at these areas, these gray spaces around the devices, look at register components, look at memory components and operating system components, look at the way that the system goes together. We then had to look at the tool chain. We had to look at how you authenticate in a tools chain. We had to look at all these components and understand it top to bottom in order to do this. Again, this was probably about 2 years worth of work to figure all the math out. We've been presenting this over the past 2 years at a couple of different conferences, and we think we're getting ready to start rolling this into some real devices probably in the next 6 months or so. So let me wrap up with a little bit of summary. What is it that I'd like you to take away today? First one point I think is important. Embedded systems are complex, but there's an awful lot of opportunity for applied security work. If that's a field that you think has an interest, I would strongly encourage you to really seriously look at it, whether it be in an academic field or an industrial field. I think there's an awful lot of stuff here to do. I've been in this field for quite a long time. As I said, it's going to be an ongoing process. I don't ever see it going away. A lot of challenge. If you're liking challenge, it can be an awful lot of fun. And I'd say encourage it, go for it. If you're there, understand the tension between product development and security engineering. Understand that what the product guy wants to do is very different what the security guy needs to do. It's okay, and you have to be able to understand that tension because you have to get the product out, but it has to meet the security requirements. Your risk analysis has to be done. Your trade-offs have to be done in an appropriate way for that particular business, and that's the direction that you need to go. Make sure that when you're looking at a system, you look at all the boundary conditions. Remember, it's gotten to the point where we're putting crypto algorithms on functions. We have SSL. We have protocols that have been analyzed now. So we're getting away from things like, the web fiasco that came out a few years ago. We understand how to do that. We understand how to analyze software applications. We understand how to analyze operating systems. These functions are absolutely coming to play in the way that the software world works. It is a transition. One of the things that we've looked at, as an example, when I was doing software development, say 18 years ago or so, we were at a place where we were looking at process, we were understanding how to develop components, how to develop new kind of products, understand things, how to do project management. So for instance, I had an example, let me just kind of touch this because some things don't ever change, they just change domains. We had a product that we were looking at. I had a software team at that time, about 45 people, and they said, we need to build this new product, has a bunch of software in it. We said, great. We looked at it, we analyzed it, we developed all of our good software practices, and we did some estimates, and we said, it's going to take this long to build. Vice President came in and said, well, that's great, except we committed to the customer that we're going to do it that long. What do we do? I was like, I think we have to tell the customer to go away because you can't build it that fast. He said, well, just go grab more software people. What's the problem? Anyone can write software. Now that was a very typical attitude that I heard an awful lot 18, 20 years ago. In fact, I almost cut my career really, really short that day because I kind of looked at him across the bench and said, excuse me, but you're a really smart, bright person. You're a vice president, been around a long time. Can you write software? I almost got thrown out of the office. Oh well. But I learned and I came back. But the problem is you can't take somebody who is an out-of-work or idle mechanical draftsman and just make them write software. They don't have the training and they don't have the skill sets. Reason I bring that up is I'm doing the same thing today when I talk about security stuff. I go in, they say, it's just security. Anybody can do security work. What's the problem? Go grab 3 people. They can think about it in their drive home and it's done. That's not the kind of stuff that we're seeing. It takes a specific set of skills, takes a different thought process and a different mindset. We're looking at very different things than the average software person is. And I think that's an important function that for us to be able to drive this in terms of its capability, we need to learn well, we need to bring that into the product space. If you're there, concentrate on the how, the why, and the if. Don't think about the why. That's not important. Yeah.
For any product, like how many people do you have working in security alone?
The question is, for a given product, how many people would I say I have working on security? Typically what I would say, I have probably about 7 to 10 working in the research space trying to develop architectural components. Probably another 5 or 6 working in kind of either applied technology or shorter in research working on applications and services. And in the product team, we probably have about 4 or 5 dedicated people there, and then probably a few people that are kind of part-time-ish on the side trying to look at it.
Is there a definite limit to the amount of security you can have on a project?
My feeling is that we're probably a good order of magnitude short of what we should be doing. Now, can you convince a product manager with a finite line item budget that that's true? It depends on how many customers are coming in and canceling orders because they don't like the security in your product. So, but I think that we're probably not where we need to be. And in fact, my team has been, I would say we've been hiring pretty consistently. I've had open recs for a good 4 years. I don't think I've ever gotten full. So, the last one is, if I can leave with one final point, and I think this is the interesting thing, and I've kind of mentioned it a couple of times. I think that you need to look at security, especially in the embedded space. It's the journey, it's not the destination. We don't ever get there. The challenge, the fun, the experience, the heartache, if you will, is all about what you do on a day-to-day basis and moving. I've been doing this, I think I touched my first security component 1981 or something. A long time ago, and I've been doing it ever since. And in some ways, we've changed the size of the systems, the speed of the systems, and the capability of the systems, but half the problems are still the same. We do them differently. We do them faster, better, smarter, cheaper, but we still have issues, and I think that's likely going to be where it goes. Again, as we make our stuff better, our adversaries make them just that much better and that much stronger. They're learning an awful lot of functions. I was at a conference, the Usenix Computer Security Conference about a month or so ago, and I was talking with a guy there who has a couple of well-known books on rootkits, and talking about rootkits for Microsoft PCs and that kind of space. And what he was talking about is like, all the guys that are kind of getting bored with writing rootkits for PCs are now starting to write rootkits for cell phones. And I said, woohoo! Another bunch of stuff to start looking at, and that's where we're going to go. In terms of contact information, there's my email if you would like to talk about some of these things or have some questions. If you look at this site, www.motorola.com TechPubs, that's where Motorola Labs at a corporate level. We publish a lot of our externally available papers on almost any type of technology you want. I know we've got a handful of them in the security space are now up in that space. You can take a look at them. Some of the papers on the protected JTAG functions are there. I know from some of the conference proceedings are available with some of the details. Or if you want to contact me, I'd be happy to answer questions. As well, I'll be around for a little bit yet after this session. So if you want to debate the points, I'd be very happy to spend some time this afternoon yet. Joel?